It's my pleasure to be here in Nanjing, and it's been a wonderful enjoying the hospitality that has been really quite remarkable, admirable. So time is short, so I'm going to switch a little more technical, close to my heart. Actually, my career, I'm coming back to my roots of propagation and measurements, and my motivation shared with the many colleagues. I'm fortunate enough that I was able to impose upon my colleagues. Which one is forward? No, okay, all right. So
you can also have this. You can free.
Oh, okay. Can you hear me without the mic, or
you need the mic? Need the mic.
I need the mic. Okay. So if you are all like me, you will know that in the early days of cellular, it was made possible because AT&T Bell Labs ran a massive series of measurements, some of them called Chicago measurements and the like. And together with researchers in Japan, in the HATA model based on measurements, I believe in Osaka, but anyways, this massive amount of measurement were able to produce this HATA model. These HATA models have been the gold standard to do coverage prediction of Morocco trails. Now, back to the future, and we're talking 28 gigahertz, 60 gigahertz, and all sort of, I would say, I would be gracious and I would call them advocates. Told us it works, it's fantastic, it's going to work everywhere. I had my doubts. But soon I became convinced that the train had left the station. There was no point in calling people's attention that penetration to walls, to metallized glass, even the F1, F2 squared that we know from fundamentals was going to limit range dramatically and eventually falsify the business case. So I had to settle by doing the hard part. Nitty-gritty, collect a lot of data so that we can develop robust models, robust in the sense that you can do predictions on a city you've never been to, and your error in your prediction after you go back and measure is still reasonable. And we are talking about standard deviations of 6 dB or so. But back to fundamentals. In order to do measurements at these high frequencies, we needed to calibrate. So we start with having antennas. I don't know if there is a pointer function here. I'll try the top. Is that a pointer? Doesn't look like a pointer. Okay, it looks like I just gave my presentation. Okay, so antenna in the echo-free chamber on the bottom left. I'll just use the verbal pointer. And so at 28, 60 gigahertz, we start by calibrating carefully, making sure we have antennas that have one direction, side lobes that are 40 dB or below. And then we take them in the open field, and in black you see it behaves as expected. However, as you move along, just the ground reflection and the direct path already causes a lot of constructive and destructive interference. So you see two-way theory, it tells you something. Of course, the phase shifts are very hard to predict, so the actual position of the mouse is not accurately predicted within the meter scale, but the general quantitative behavior is there. Okay, so we have an instrument that we can use to make this data collection, and I took the choice of privileging lead budget over more fancy. I mean, at the time, there were some very fancy sounders or VNAs, but they can only work within 10 meters or so, or they need to be connected transmitter receiver with a cable. We wanted to test the promise that has been made that you can go long distances at these frequencies and still have good coverage, which is the key for financial success. So we worked very hard to have a 171 dB link budget, and with a 10 dB measurement SNR, so we have high quality measurements, and we use a rotating horn so that we can, for the first time ever, record at these frequencies power versus angle. At the top right, you see the receiver. It's mounted on a table. Everything is actually on top of the table. One advantage of this higher frequencies is that everything is becoming so small. So we can keep it there and rotate it and talk to it, control it, and download the data over Wi-Fi. And at the bottom right, you see the transmitter, which is extremely simple because, as I said, we privileged link budget. So we have a very narrow 20 kilohertz signal bandwidth, so we filter out most of the noise. So with this instrumentation, we're set up to collect data. For a number perhaps remember, this is Crawford Hill. On the back, not far from the antenna that was used to measure the 3-degree Kelvin for cosmic radiation. But let me not get into that because I could speak for the rest of the day and we don't have the time. So at the left, you see the rotating unit, the table on top, and you see a horn and you see the electronics. And in the middle, you see a transmitter. It's very simple with a horn antenna. And in the far right, you see with an omni antenna that is even simpler, of course. So with this, similarly at 60, everything gets a little smaller, but in the interest of time, please stop me and ask questions later if you like, and maybe I can save a few minutes for questions. But we set out to make measurements in a wide variety of locations. And Nambi again would remember the top right is our corridor, DRS corridor that we've used for measurements way back at 2 gigahertz and ray tracing and all of that, but that's ancient history. But we went to streets in Manhattan. Many measurements are needed to make robust models. I want to emphasize that. You can go out and do 40 measurements and discard 20 because we didn't have enough link budget, and then you write a paper on the remaining 20 data points. Cool, and you get away with it if you are the first. That's the beauty of being the first. But when you're the second, then you have to do 90% of the work for 10% of the credit. But that's life. So we were second, so we were doing 90% of the measurements. So we did outdoor streets, same street, around the corner, factory, and measurements also target for fixed wireless access. So what do we get? Well, in corridors, surprise, surprise, corridor has a guiding effect, so it's actually better than free space. Okay, as expected. However, at the right, what happens if you turn the corridor? Oh, wow, look at that drop. Going around the first corner, then going around the second corner. So dramatic signal drop as you go around corners. So it's a good news, bad news story. It becomes very site-specific. So if you happen to be in the same corridor, you're better than free space. But if you happen to be around the corner, now you're sustaining tens of dBs. In the scale there, 10 dB per division. Every corner is close to 20 dB of additional loss into your link budget. So your coverage becomes a disaster. Now, on the left, of course, just a sampling of the data collected, and different colors just means different data collection runs, and the regression, and I can talk forever, but I can tell you no existing 3GPP model was a good fit. So we really need to do new models for this purpose. So in Manhattan, it becomes much more relevant for business. So if you wanted to place a 28 gigahertz co-located with the existing base stations, which is the absolute requirement by service providers. If you don't do that, then they don't want to listen to you because it would break their bank. So you have to be co-located, and so we use the balcony at Columbia University. We have very successful collaborations with various universities, and this balcony is a stand-in for a base station, and as you see in the picture on the right, we make measurements along the dotted line, transmitter promenading along the street, and the receiver rotating and capturing the data power versus angle. So by looking at the angle that gives us the biggest power, then we plot on the left. And you can see non-line of sight urban macro is too pessimistic on 3GPP, the black dot line, while line of sight urban macro is too optimistic. Reality is somewhere in between. So this is all very good learning lessons. No existing model, it's giving you an accurate model. And by the way, we tried ray tracing as well, and believe me, I'm an early fanatical of ray tracers, but not surprisingly at these frequencies, in line of sight, it's too optimistic because it pretends that line of sight is truly line of sight. There is nothing there unless you take a tremendous effort to digitize everything in the street, which is not practical. And then around the corners, it becomes too pessimistic because it thinks that there is nothing to scatter the power around the corner, when in reality there is plenty. So don't believe ray tracers either, which, by the way, they tend to be used to do digital twins, so word of caution with digital twins, trustworthiness. But anyway, I digress. Look at this, fascinating. What happens if you are out in the street? And no business case could survive if you do not turn around corners, at least a little bit into the surrounding street, because otherwise you would have these dark shadows, or you'd be forced to put antennas at every possible intersection. Can you imagine the cost of doing that? So look at here. You are going down the street, and then boom, first turn around the first corner. You are going around the red on the right, so that we call same street. We no longer call it line of sight, because same street, there's always something there to make it worse than true free space line of sight. But you're going along, and then you make a left turn into the blue. And so here you see the round circles, actual measurements around the blue. And of course, the curves are all theory based in electromagnetics, proper treatment of diffraction, and so on. And then, or you can continue along the red and then make a turn on the yellow, and boom, you get a very repeatable behavior. Or you can continue on the red and then make turn on the green, boom. So we are onto something. We think we understand what's going on with turning around corners in Manhattan-like environments. So this is where the groundwork of collecting a lot of data starts paying back, because you can connect the dots, literally. And if you have good theory, that's the connection for you without doing any coaching or graphical manipulation, then you are onto models that are robust. So moving on. Okay, all right. So factories, again, a lot of data points. Again, no existing 3GPP, whether dense, low, or other types of 3GPP models was a good fit. There is a sparse model and there is a dense low model, but you see here with a tremendous amount of data, you find that number one lesson, it's spread over 14 dBs, even at 50 meters, which is not very far. And factories tend to be rather open spaces. We're not talking here, iron smelters or very large metal objects. We're talking more like electronic assembly, imagine that. So pretty open spaces, but there's a lot of stuff around, filing cabinets, tools, etc. So the cloud is very spread out. And so that when you do your coverage prediction, you would need to account that in your fade margins if you want to have 90-95% coverage. So again, 3GPP models give you errors that are from 8.8 to 15 dB, and we can do a lot better with the models based on this data. The next one was fixed wireless. Again, colleagues generously offered access to homes. I think it's in the bottom right, there is GenFem there, and you see in the red circles surrounded by yellow, antenna emulating what could be perhaps a fixed wireless access antenna, or on the top right, same idea. While in the street, we're moving this telescopic mast with the rotating receiver on top. And you can see again the data, or a massive amount of data collected, going all the way to 200 meters, more than 1,700 links, again in collaboration with another university from my country of birth in Chile. And so very good data, very reliable. Now, here is again the news I have for you. It turns out that to our amazement and discovery, and I'm not going to go through every single one of these examples, but let me attract your attention to the right. So 3GPP model is the dash in red. And then on black, you see the dreaded low E glass. So you see a lot of penetration loss. To the right is worse. And to the left is better, right? So green is old-fashioned plain glass. Then from green we go to the purple, low-loss material. It's close to the low E window, which is the modern, tend to be used a lot of in northern countries. But look at that gap. That's 5-7 dB at the median of extra loss, depending on what kind of glass we're talking about. So how are we going to do accurate coverage prediction if we don't know what kind of glass? Do you think the service provider is going to be calling, oh, you want a fixed service? Can you tell me what kind of glass is your house? I don't think so. Most people don't even know. So site-specific, material identification, these are huge headaches for reliable coverage prediction. So moving along, you heard the advocates promise that we solve all the problems of high frequencies with directive antennas. And biggest than any much that are very interesting, the problems that I mentioned so far, they were order 5, 15 dB. But what's called the F1, F2 square, which is the fundamental loss in free space, is proportional to the square of the ratio of frequencies. So if you double the frequency, you lose 6 dB at 1 meter right out of the bat, even if you are in deep free space with no scattering, no nothing. Now, it's true, if you have keep the aperture of the antennas at both ends, you can more than overcome this loss, as some had greatly advocated this to solve all these problems. The trouble is we are not in free space. So we have this feature, put it that way, or challenge that we call the antenna gain degradation in scattering environment. So, and I can explain it to you very, very simply. So if you are in truly free space, imagine a dark night, there's nothing around, you shine a laser, and the laser goes almost forever, it hits a wall, and you see a nice demarcated green spot. Now imagine the same scenario, but you are surrounded by fog. You point the laser, and the laser scatters around in every single water droplet, and all of a sudden you're surrounded by a green glow. Now, in the first case, you could point an antenna and select that narrow angular direction that the spot, and filter out everything else. In the case that you get the entire fog illuminated by green, every time you're trying to narrow, to filter out, quote unquote, the noise, you're leaving out energy that was supposed to be good energy. So in the isotropic Rayleigh scattering environment, antenna gain is 0. Because anything that you can gain, you're losing by not collecting the antenna that is coming outside of your beam. The other way of saying that is the lighthouse. Lighthouse looks like a lighthouse when there is no fog. But when on the right, I'm trying to illustrate with light here, when there's a lot of fog, it's no longer a beam. So your beam gain is gone in the presence of scattering. Well, that's a nice concept, but does it happen in reality? So here I show a sampling of indoor office, suburban, factory, and urban Manhattan. If the antenna gain was deterministic free space, you would see a vertical line at the nominal antenna gain, which we can indeed measure in the echo-free chamber. So for instance, it becomes very clear in the bottom far right, that vertical red line at 14.5 dB, that is the true antenna gain nominal measured in free space. But let's put the same antenna now in realistic environments. And to make it dramatic, if you're in one line of sight, so the second from the right, and in the blue CDF, you notice that if you want to do calculations that are giving me confidence to 90% of the potential customers, I have to penalize that antenna with 7 dB. Because the original nominal antenna gain of 14 in the real world of scattering is actually only 7. So this is real, it's measurable, it's repeatable, it is site-specific, so sometimes it will be 4 dB, 7 dB, 6.6 dB, depending on the environment, because it depends on scattering, and scattering depends on the environment. So it's not the end of the world. You know, you lost 7 out of 14, you still have 7. But as you make the antenna even further narrow, the problem is going to get worse. In fact, at some point when the antenna is commensurate with the environment natural angular spread, you will see no longer antenna gain as you try to make it narrower, because you are going to be in that space where you are trying to cut it narrower than the cake sectoral width. And so whatever you try to save in noise, you're leaving cake material outside that you're not going to eat. So, good news, bad news. Be careful when you say you're going to have 40 dB of antenna gain. That is something like sub 1 degree narrow. And so in the real world, you're not going to see that gain. In free space, point to point, maybe. Okay, so I think, okay, here. All right. So another interesting observation is factory, and this is a good story. In factories, there was a lot of concern, mostly from our protocol friends, that you're going to be blocked, the blocker, the dreadful blocker. So you have a beam pointing to a robot, and then somebody crosses the beam, and everything, disaster happens. Well, in reality, real world is complex. Things are not that simple. And you block one ray, there are 99 other rays that can save the day. And this is exactly what I'm trying to show here. So we did a deliberate blocker of a metal object that we moved at various distances. And I'm out of time already, so what I can tell you is that, yes, if the blocker happens to be within 2 meters of your antenna, yes, you have a 10 dB effect. But it only takes for the blocker to be beyond those meters that the effect is order 2 dB. So means that the environment is rich enough that once you move a reasonable distance, there'll be other paths that are going to save the day. So forget about blockers causing retransmissions on layer 3 and everything goes to pot just because somebody walked into the beam. It doesn't happen. If you have a few dB of link budget, and if you perhaps put the antennas high so that people don't really block them at a very close range. But I don't want to abuse you guys' patience. You've been a very nice audience. I wanted to leave some time for questions, but I guess I didn't. But feel free to stop me, and I'll be very happy to engage in conversation outside.